Hi students, welcome to my lectures on chemical reaction engineering. In the last class we have discussed about the design equation for batch reactor and small problem. In the today's lecture we are going to discuss about one more reactor which is a continuous reactor called continuous stirred tank reactor. Unlike that of a batch reactor, in this reactor there will be continuously feed that is coming in, that is continuously the product that going out. So, there is no fixed volume because the volumetric flow, because feed will be coming into the reactor at certain volumetric flow rate and feed will be going out of the reactor at another volumetric flow rate. So, let us discuss, because our objective today is to find out what is the volume of this continuous stirred tank reactor for 50% conversion or 60% conversion or 70% conversion. Let us do that. And let us define some terms before we go actually into the derivation part. Here is your reactor, just like the batch reactor, but now it has the two ports, one is inlet and one is exit. FA0, CA0 and V0 are, FA0 is the molar flow rate, how many moles every second going into the reactor. CA0, what is the concentration of reactant A, that is moles per liter in that volume. V0 is the inlet volumetric flow rate in liters per second, that is per second how much amount of liters of the reactant going into the reactor. Similarly, FACA nu, or FA is the exit molar flow rate of A, Ca is the exit concentration of A that is remained after the reaction, and nu is the exit volumetric flow rate of A. Here the equations will differ whether what phase reaction is going on. Example, if the liquid phase is inside the reactor, then the inlet volumetric flow rate will be equal to exit volumetric flow rate. There is no change because of the reaction, because liquid volume will not change because of the reaction. But if any gas, that is gas phase reaction is happening, inlet volumetric flow rate is different from the exit volumetric flow rate, because example, 1 mole of A is giving 1 mole of B, there is no change in the moles, so no change in the volume. But imagine 1 mole of A is giving 2 moles of B. That means before the reaction it is 1 mole, because of the reaction it is 2 moles now. Suddenly the moles will increase, the volume will increase, volumetric flow rate will increase. The other situation is 1 mole of A is giving half mole of B. That means before the reaction it is 1 mole, after the reaction it is half mole. That means the volume, because moles is large before the reaction, so the volumetric flow rate before the reaction is higher, volumetric flow rate after the reaction is lower. So that is because for the gas phase we need to take a special care. For the liquid phase it does not matter whether 1 mole is giving 1 mole, 1 mole is giving 2 mole, 1 mole is giving half mole, liquid volume will not change. So inlet volumetric flow rate is equal to exit volumetric flow rate. By keeping this basis in mind, let us go and derive the design equation of a continuous stirred tank reactor. And the starting thing is the mole balance on A. That means I am applying the mole balance on the reactant A. This is like the case of the batch reactor. Moles in, that means moles that is coming into the reactor, moles out, that means moles of A that is remained after the reaction that is coming out of the reactor, moles of A that is generated, because A is my reactant, A will not get generated. So this term is equal to 0, minus moles consumed per second. That means because of the reaction, of course the moles of A will come down. So that is why it is a minus moles of A, and remained, that is nothing but moles accumulated per second, because it is steady state operation. That means with respect to time nothing changes, because continuously the feed is coming in, continuously the product is going out, there is nothing that is stopping in between. So with respect to time nothing is changing, that is why nothing will accumulate every second. So that is why this term is equal to 0. And moles in per second is nothing but my molar flow rate of A in, moles out is nothing but molar flow rate of A out minus moles consumed every second. Moles consumed means who will decide how much amount of A, that is how fast the A will consume depends on the rate of reaction or speed of reaction. That is why minus Ra into V will decide how much moles of A will consume every second, because the rate, units of the rate is mole per liter per second into volume of this reactor will become liter. This liter cancels out. Finally, every term should be in moles per second. Now this is my mole balance. Now take volume on one side and rest terms on the another side. So V is equal to Fa0 minus Fa by minus Ra. This is my design equation. One more thing you have to remember, the concentration of A in the reactor, which is equal to the concentration of A that is exiting the reactor because of the stirring effect. So whatever may be the concentration of A that is in the reactor, that is the same amount of A that is coming out of the reactor. Ca0 is the initial concentration. So let us come back. So volume, you know the design equation. I know Fa is equal to Fa0 into 1 minus x. If I substitute 2 in 1, I get volume of the reactor is equal to Fa0 into x by minus Ra. These two are my design equation. That means it can apply to any order, okay? It can apply to any volumetric flow rate, and these two equations are called generalized equation. That means this equation applies to all order reactions. Now let us take a small turn now. This equations, generalized equations, applies to all orders, all reactions. What happens if it is a liquid phase reaction, and what happens if this is a gas phase reaction? Let us deal with them. And I told you, if it is a liquid phase reaction, the exit volumetric flow rate and inlet volumetric flow rate will not change. That means volume change because of the reaction will not happen. So that is why liquid phase reaction, we nu 0 is equal to nu. Otherwise constant volume reaction, okay? Epsilon, any value, normally epsilon will decide whether volumetric flow rate increase or decrease or remain the same. Epsilon is the factor that decides. Example, 1 mole of A is giving 1 mole of B, the epsilon means product moles minus reactant moles, which is 0. That is, there is no change. I mean, inlet volumetric flow rate will be equal to the exit volumetric flow rate. If it is 1 mole of A giving 2 moles of B, that means epsilon is equal to 2 minus 1, which is 1, that is positive. Positive means the exit volumetric flow rate will be higher than the inlet volumetric flow rate. Epsilon negative means our exit volumetric flow rate will be less than the inlet volumetric flow rate. That epsilon decides whether volumetric flow rate will increase or decrease or remains the same. Okay. Now the thing is, it does not matter epsilon any value, as long as liquid phase reaction is there, there is no change in the volumetric flow rate whether epsilon is positive or negative or equal to 0. So that is why at any value of epsilon, let us do for a first order reaction how I can able to find out the volume of the reactor. I know, example, if first order reaction is happening in the reactor, then A gives rise to B, minus Ra equal to Kca, you know, Ca equal to Ca0 into 1 minus x. Substitute here in place of rate, you get minus Ra is equal to Kca0 into 1 minus x. Now use the generalized equation, substitute the value of the rate in this generalized equation, and you get V equal to Fa0 into x by Kca0 into 1 minus x. Now Ca0, I know my initial concentration is equal to molar flow rate divided by volumetric flow rate. How? Molar flow rate have the units of moles per second, and volumetric flow rate have the units of, example, liter per second, okay, liter per second. Now you get second cancels, the concentration is nothing but mole per liter, okay. Substitute in place of Ca0, Fa0 by nu 0. and a few terms which cancels out. Finally, the volume of the reactor is nothing but nu 0 into x by k into 1 minus x. That means if you want a conversion, that is for 50% conversion, how much volume of the CSTR is needed, you can get from this expression, provided if you know the rate constant of the reaction and volumetric flow rate. For a given volumetric flow rate, if first order reaction is happening, how much volume of the reactor that is needed given by this equation. And another term in the process we have to define is space time. Okay. Example, what is the space time? If V is the volume of the reactor filled with V amount of liquid, example V is equal to, example if I have 2 liter liquid is there in the reactor, how much time this entire 2 liter liquid will come out of the reactor during, because everything is coming in, everything is going out. So let us assume that I have the 2 liter reactor. For this entire 2 liter to come out of the reactor, how much time that is needed? Okay, that is called the space time. Sometimes the space time has the value in the reactor design. Let us do that in the later state. How I can get the space time? If you divide this volume by volumetric flow rate, the unit of volume is liter, volumetric flow rate is liter per second, liter cancels out and second comes to the numerator. Finally, tau is denoted by space time. This tau is nothing but volume of the reactor divided by volumetric flow rate is nothing but x by k into 1 minus x. This is for the first order. Okay. This is how you can able to use, you can use this equation number 7 to find out the volume of the reactor, equation 8 to find out the space time for the reactor. Let us do the same thing for the gas phase reactions. Gas phase reactions are those where exit volumetric flow rates may not be equal to the initial volumetric flow rate. That is why nu 0 is not equal to nu. Where then the other name is variable volume reaction. Okay, epsilon not equal to 0. That means 2A gives rise to B or A gives rise to 2B. These are called variable volume reaction, because here the epsilon is equal to 1 minus 2, that is minus 1. Here it is epsilon is equal to 2 minus 1, this is 1. If it is not equal to 0, then we have to apply that too, that is a gas phase reaction. You have to go through this process. Okay, right. Let us do that. For a first order reaction, minus Ra equal to Kca. Ca equal to Ca naught into 1 minus x by 1 plus epsilon x. This is the additional term that comes when it is a epsilon not equal to 0, and that too it's a gas phase reaction. For liquid phase reaction, it doesn't matter what is the value of epsilon. For gas phase reaction, if epsilon equal to 0, then there is no problem. If epsilon not equal to 0, then you have to use this expression. This expression comes from my stoichiometry lectures, then you can able to go back to my lectures and see how this equation has come. Substitute in place of Ca this entire term, minus Ra equal to Kca 0 into 1 minus x by 1 plus epsilon x, and substitute in equation number 3 the equation number 8. You get volume is equal to same procedure. The volume is equal to nu 0 initial volumetric flow rate into conversion into 1 plus epsilon into x divided by k into 1 minus x. See the difference here. If you make epsilon equal to 0, that means if there is no epsilon, liquid phase reactions, there is nothing. Here the additional term has come, 1 plus epsilon x. Okay, that is what the basic difference as such between the liquid phase reactions and the gas phase reactions. Liquid phase reactions epsilon will not come, gas phase reactions epsilon will come. Similarly, volume by volumetric flow rate is nothing but x into 1 plus epsilon x by k into 1 minus x. That is what the tau. This is a space time for the liquid phase reaction, this is space time for the gas phase reactions. Okay, I hope now you can able to judge. Okay, you can able to design the volume of the reactor, you can able to find how much time that is spent by liquid molecules in the reactor. Here also you can able to find the volume of the reactor for the gas phase reactions, and finally space time for the gas phase reactions. Let us define the space time in official sense, and time required to process one reactor volume of the feed. That means how much time it takes one reactor volume, to come out of the reactor. Because to process means one reactor volume came out means already 1 liter reaction already been taken place in that 1 liter volume. So time required to process one reactor volume of the feed. Okay. Example, if volume is 1 liter, volumetric flow rate is 1 liter per minute. What is space time? That is nothing but volume by volumetric flow rate, 1 by 1 minute. That means 1 liter volume. That means if the reactor volume is 1 liter, it takes 1 minute for this entire 1 liter to come out of the reactor. Example 2, volume is equal to 1 liter, volumetric flow rate is equal to 0.5. That means I have reduced the flow into the reactor. What happens? My space time, volume by volumetric flow rate is nothing but 2 minutes. That means if I reduce the velocity or volumetric flow rate of the flow into the reactor, the same 1 liter volume of the reactor to come out, it takes 2 minutes, because I have reduced the volumetric flow rate. Here volume is 1 liter and volumetric flow rate is 1.5 liter. That means what I have space time, 0.6 minute. That means same 1 liter volume of the reactor, this 1 liter volume to come out of the reactor, it takes only 0.6 minute. That means it even because the flow rate is high, it takes less time to come out of the reactor. So that is what the importance of space time. And how it is important in the sense, if you increase the space time, that means the conversion will increase. How? That means if a molecule is spending more amount of time in the reactor, the conversion will increase. If the molecule is spending less amount of time in the reactor, the conversion will reduce. So that's what the importance of space time. Let us do a small example for the liquid phase and the gas phase reaction. So you will realize the importance of the flow rates and space times and concentrations, rates. Let us do that. And let us solve the problem. On this side of the board I have solved for the liquid phase, on this side of the board I have solved for the gas phase for the same variables. Example, I need to find out what is the volume, what is the space time, what is the concentration, what is the speed of the reaction, rate of the reaction happening in the reactor. If it is a liquid phase first order reaction is happening, given the molar flow rate is 2 moles per second, volumetric flow rate is 0.1 liter per second, and rate constant for the first order reaction is 0.016 per second. If I know, given the parameters, I need to find out what is the volume of the reactor, space time, concentration, rate for 50% conversion. That means for 50% conversion, what is the volume that is needed, okay, for the CSTR. I know Ca0 equal to Fa0 by V0, 2 by 0.1 is 20 mole per liter. X given for the conversion is 0.5. Let us use the equation number 7 to find out the volume is nothing but volumetric flow rate into X by K into 1 minus X. If you substitute the values, you get 6.25 liter. That means for 50% reaction to happen, you need at least the volume of the reactor is 6.25 liters. Let us find out the space time. Okay. In the space time, just a second, volume by volumetric flow rate and X by K into 1 minus X. 0.5, if you substitute the values, that is 62.5 seconds, that is 1 minute. That means it takes 1 minute for this entire volume to come out of the reactor. The space time is this much. What is my concentration? Ca equal to Ca0 into 1 minus X, that means 10. My initial concentration is 20 here. The final concentration after 50% conversion is 10 mole per liter. What is the speed of the reaction? Is nothing but Kca. K into Ca, that is 0.016 into 10, that is 0.16 mole per liter per second. We have calculated everything. Okay. Let us do the same calculation for the gas phase reaction. Now it is a gas phase reaction. I mean, given the reaction A gives rise to 2B, the given. Okay. Now my epsilon is equal to 2 minus 1, this is equal to 1, not equal to 0. If epsilon is not equal to 0, that too for a gas phase reaction, my inlet volumetric flow rate will not be equal to the exit volumetric flow rate. In such cases, let us find out how much volume of the reactor is needed for 50% conversion. Same. Here also for 50% conversion, here also is for the 50% conversion. And same, Ca0 equal to Fa0 V0, but initial concentration is equal to 20 mole per liter. Volume V0 into x into 1 plus epsilon x divided by k into 1 minus x. Now my volume is 9.37 liters. Here for 50% conversion, 6.25 liter reactor is enough. Same as for the same conversion for the gas phase reaction, I need more volume. What is space time? Okay, and volume by volumetric flow rate x into 1 plus epsilon x by k into 1 minus x. 187.5 seconds have come, that means 3 minutes. That means the space time, that is time required for one reactor volume of the feed to come out is 1 minute. Here it 3 minutes because volume is higher now. Okay. For the same conversion, it needs higher time to, because I mean the volume is now the volume has been bigger. For the same conversion, it takes more time. Okay, for this entire volume of the reactor to come out. Okay. Now concentration, Ca equal to Ca0 into 1 minus x by 1 plus epsilon x. It is 6.6 mole per liter. This is my exit concentration. Here the exit concentration is 10, here the exit concentration is 6.6. That is the reason you need higher volumes for the same conversion, because you know the volume of the reactor decided by how speed the reaction is happening in the reactor. The how speed the reaction is happening in the reactor decided by the rate of reaction. Here you can see the rate of reaction is 0.16 mole per liter second. Here the rate of reaction is 0.1 mole per liter second. Here the speed of the reaction is very high because the concentration, exit concentration is high. Here the speed of reaction is very low because the exit concentration is very low. So that makes, if the speed of the reaction is very slow, I mean slow, you need, for the same conversion, you need bigger volume reactor. Okay, that is why here for the same conversion, 6.25 liter reactor is enough. Here for the same conversion, 9.3 liters reactor is required. So this is what the differences that comes when it case of liquid phase reactions and gas phase reactions. Okay, we need to be very careful. Okay, whenever you see gas phase, that means epsilon factor you have to think. Okay, finally epsilon factor that comes everywhere, which decides the volume, which decides the space time, which decides the speed of the reaction. Okay, I hope you have understood the continuous stirred tank reactor design. Let us meet with the new lecture.